بس أنا هاني باش نسكر المايك وباش معناتها نحط معناتها الافيش متاعها ونحط شوية موسيقى ونبدأ ندخلهم.
D'accord.
اوكي أدت على أخ.
And welcome to our Asset lecture.
Sani, you can start.
Okay. Hello everyone, and welcome to our Astro Talk lecture, which is organized by the Tunisian Association of Young Astronomers, TAYA. I'm Sanaya Ayari, and I have the pleasure to be your chair in this session. So we're gonna wait until the other participant come. No, doctor, I can't hear you.
Dr. Randa, we can't hear you. Like, I think you have a problem in your mic because I even cannot see your mic. So you just need to cross to activate it.
Oh, okay, so can you hear me now?
Yeah.
Okay.
So today's lecture it's about the chemical history of galaxy, which is going to be written by Dr. Randa Asad. Welcome, Doctor, and it's such a pleasure to have you with us today.
Thank you. So should I start?
So allow me to represent you to our audience.
Yeah, sure.
So Dr. Randa Asad is an assistant professor at the American University of Sharqa. She obtained her PhD in physics from the University of Cincinnati, Ohio, USA. Her research interest is focused on modeling observed spectra of distant star cluster to trace the chemical enrichment history of galaxies. She has been invited as a visiting researcher at several renowned astrophysics research centers, such as the Harvard Center of Astrophysics, the Space Telescope Science Institute, and the ESO headquarters in Munich. Dr. Asad have the opportunity to spot the distant star cluster in some of the world's most advanced and sought-after telescopes, including VLT, Lumin, Magellan, Blanco, and Thor. Her research is presented at the international conference and published in the most important astrophysics journals. She also a member of the American Astronomical Society, the International Astronomical Union, the American Association of Physics Teachers, the Arab Astronomical Society. She has been honored as the Woman of the Week at the University of Cincinnati in 2012 and won first place in a poster competition at the same university. So the floor is yours, Doctor.
Thank you so much for this introduction, and it's my pleasure to be here and share my research with you. So I'm going to share my screen. Okay, do you see my presentation?
Yes.
Can you see it? Yes, okay, good. Okay, so today I'll be, first of all, I want to thank the organizers for inviting me to give this talk. And today I'm going to be talking about the chemical history of galaxies. And just before we start, I want to talk a little bit about some motivation of why I'm interested in giving this talk. So hopefully this is not going to be just like like a regular talk. I want it to be a motivation for our youth. One interesting thing that I've been noticing over the past few years is that there is a lot of interest in the field of astrophysics among our youth. So this is something very positive, and I really admire the work of different organizations. And so the organizations both do outreach activities, which is trying to get to people who maybe don't have that much of background in the field, but also the organizations that try to do like seminars and presentations and events like this. So I want to give a special thanks to Taya for organizing this event, and to be for being very patient with me, because there were some discussions back and forth and some details and so on. So I really apologize for that, and I'm very happy that this event is finally taking place. The reason I said that I want this to be a good motivation for you is that we all talk about the contribution and the achievements of Arabs and Muslims in this region in the past, and we're all very proud of it and we like to talk about it. But what I want every one of us to think about is, how can we have our own contribution? So instead of just looking and reading about the achievements of others, we can have our own achievements. And I want to invite you today because, as we all know, there are still many open questions that still don't have answers, and they're waiting for you and for me and for every one of us to try to find the answers for these questions. So I want to remind everyone that whenever you hear a talk and you hear about a new area, you have a lot of potential in that specific area. All you have to do is to pick the area that you like most, and then try to aim to answer questions in that area. Yeah, so my talk today is going to be about one of these fields, or one of these open questions in the field of astrophysics. Okay, so let's start with the very basics. What do we know about the chemical composition of the universe? Because our goal, as you might remember from the title, is that we're trying to understand the chemical history of galaxies, which means that the composition of galaxies and stars is not the same. The composition that we see today is very different than the composition that we had at the time of the Big Bang, for example. So as we know, it all started with a Big Bang. At the time of the Big Bang, which is not exactly the time of the Big Bang, but when the first generation of stars formed, the composition was about 75% hydrogen, 25% helium, and a very, very small portion of the light elements that come in the periodic table after helium. If you compare this to the current composition of galaxies and stars, you will see that today, the stars that form today, they have roughly the composition of 75% hydrogen, 23% helium, and 2% of all the remaining elements. So if you look at these 2 points here, when you compare the first generation of stars with the current generation of stars, you will see a difference in 2 things. One is the quantity. So initially we had 25% helium and a very, very, very almost negligible percentage of the light elements. But also I want you to see that not only the quantity, but also the quality, or the type of elements that we have changed. Initially, it was, as I said, just these 3 elements, but now we know all these elements like iron, calcium, magnesium, and so on. All these elements did not exist at all in the first generation of stars. So the question becomes, first, how did this composition change? And where did all these other elements that we all know now come from? And as we might know, the answer is stars. We know that stars have nuclear reactions in their core. So the result of these nuclear reactions will produce new elements. And oh yeah, so by the way, this is a funny picture that I like to share about the periodic table of elements in astronomy, because we know in astronomy we mainly focus on hydrogen and helium, and everything else that's heavier than helium is called a metal in astronomy. So that's why when we say that we want to study the chemical composition, basically we're studying the metallicity, which is the composition or the percentage of all these elements that are heavier than helium. Okay, so now to understand where these elements are coming from, let's remind ourselves about the stellar evolution. So we have 2 types of stars. If we want to roughly make 2 groups. So the first one is the low mass stars, like our own sun. And we know that our sun is currently in the main sequence phase, which means that in its core, it's fusing hydrogen into helium. And as long as this is happening, the star or the sun is stable. And that's why we wake up every morning and see the sun the way it is. Nothing significantly changes. However, at one point, as it's fusing this hydrogen into helium, the sun will run out of hydrogen in its core. So at that point in time, there will go to be some changes. And that is that the outer layers are going to expand and the inner core is going to shrink. So what we see when, so if there are any questions, because I don't see the chat, so if there are questions, please use your mic. Are there any questions? Because I hear a sound, but I don't know if that's because it's a question. Okay. Okay. So yeah. So the sun, once it runs out of hydrogen, is going to from the outside is going to expand. The outer layers are going to expand, while the inner core is going to shrink. When that happens, the core, as it shrinks, of course, that means that the pressure is increasing and the temperature is increasing. So now the core that is mainly made of helium is going to reach the temperature needed to fuse helium into carbon and traces of oxygen. So during this phase, in the core of the star, helium is going to be fusing into carbon and oxygen until, again, the star runs out of helium in its core. So what's going to happen is that the same thing is going to take place. The inner core is going to shrink and the outer layers are going to expand. But the end of the story is about to happen now, which is that the core of this star, although it shrinks, it will never reach the temperature needed to fuse carbon. So the ultimate fate of our sun, or any low mass star like our sun, is going to be what is called a white dwarf, and that is a core made of carbon. So that is the core, but what we care about the most here is the outer layers. The outer layers that we see here are going to keep expanding and expanding and expanding, and then they would go just peacefully into the outer space. And that is what we care about, because if we think about the chemical composition of this, the outer layers, we will see that the chemical composition has changed from the time where the star first formed. So keep that in mind. The other type of stars are the more massive stars, or the high mass stars. In this case, the story is going to be the same in the beginning. We're going to have hydrogen in the core, and then this hydrogen is going to fuse into helium. But the story continues here. So once the core has reached the phase of having carbon in it, because it's a high mass star, it's going to shrink, and then the temperature needed to fuse carbon further is going to be reached. So then we will go in this different phases of getting heavier and heavier elements. And this will continue, as we can see here. It's going to become like different shells, until we reach the phase of having iron in the core. But as we know from physics, iron is the most stable element. So when the star has iron in its core, it cannot continue this process. It cannot sustain itself anymore. So eventually it's going to explode. That explosion is called the supernova. Okay, so as I said before, that it's going to go through these different phases of going from one element to the other, and then eventually, when it reaches iron in its core, it's going to explode. The outcome of this explosion, it's either a neutron star or a black hole. Although these are a very interesting topic to most people, what we want to focus on here is the supernova, not the neutron star or the black hole, because now, sorry, I'm going to come back to that in a minute. Now, when we look at the different masses of stars, as I said before, they will have different lives. So the the low mass stars, like our sun, as we said, is going to end up in a planetary nebula. So a white dwarf in the core and peaceful ejection of its material into the outer space. However, the high mass stars will explode. So the end is going to be different. And that is what we call a supernova. But the point is that no matter what happens at the end of the life of a star, what we care about is that the new interstellar medium that we will have after these stars live their life is going to be enriched. So enriched chemically. So if you think about the chemical composition of this interstellar medium from which these stars formed, and then compare it to this interstellar medium, you will see that this new interstellar medium is enriched, because all these elements that formed into the core of these stars will be ejected or brought back into this interstellar medium. So the point is that what we conclude from here is that as new stars form, these new stars will have a heavier chemical composition, or what we call an enriched chemical composition. Now, there is one more type of stars that enrich the material, and that is what we call the type 1a supernova. And that is when we have a binary system, which means that we have two stars that are relatively close to each other, they're gravitationally bound to each other. And as you might remember from this here, so we said that low mass stars will end as white dwarfs. But the white dwarf, the time that we reach the white dwarf depends on the initial mass of the star. So if we have two low mass stars, but one of them is more massive than the other, that more massive star will become a white dwarf first. So this became white dwarf. The other one, its companion, is still a red giant. So what happens is that because the red giant is expanding its outer layers, the white dwarf has more gravity, so it's going to pull material from the red giant, and it's going to keep doing this for so long until, again, it cannot sustain itself anymore, so it's going to explode. And that's why we call this a supernova, but this is a different type of supernova. This is coming from a low mass star. The condition is that we have to have a binary system. The other one comes from only one star, and the condition is that it has to be a high mass star. So all these types of ending the life. Yes. Yeah, so all these types of ending the life of stars will enrich the material with different elements. And that's what we want to analyze and study so that we can try to get an idea of how this is enriched, like what's the percentage of these elements that enrich the material. Okay, so now the question becomes, this was all a background about where the chemical elements come from. Now the question becomes, how do we study the chemical history of galaxies? If we think about it, we need two components. The first component is that we need the chemical composition, because that's what we are trying to study. And the other component is the age, because by knowing the age, we can have an idea about history. So for example, if I ask you, what is your history? You will tell me, for example, when I was 7 years old, I started school. When I was 14 years old, I went to high school. And then at 18 years old, I went to the university, and so on. So that's exactly what we want to do for tracing the history of a galaxy. We want to see how the chemical composition changed at different ages in the galaxy. And this can be done by studying what is called a star cluster. So the star cluster is a group of stars that are gravitationally bound together. And these are some images of star clusters. So you see that they're very nice and very luminous. They're nice to see, but they're also very useful to study because they give us a lot of information. Okay. Now, in order to study these star clusters, there are two main methods. The first method is called using resolved stars. So as you might guess from the name, resolved stars mean that I can look at each individual. So you can think about this star cluster, for example. So look at each individual star in this star cluster and try to analyze it and get the age, the overall age, and the overall metallicity of the star cluster. That is one method, and this is done, it's called, as I said, using resolved stars. The other method, and that is what we need to use when the stars are too far away, if we cannot see the individual stars in the cluster, like for example, if you see this cluster, you cannot even count how many stars we have. So it's very difficult to get individual stars. So what we need to do as an alternative is to use what is called the integrated spectrum. Integrated spectrum means that instead of studying each individual star in this star cluster, I will study the cluster as a whole. So my whole cluster is going to be one object, and I get one observation for this entire object and study it to extract information about the star cluster. Okay. So now, maybe this is something familiar to some of you, those of you who took any astronomy course. The way we study the age of a star cluster is by drawing what we call the color magnitude diagram, or the HR diagram. And that is that so again, just to remind you, we are first starting with resolved stars, which means that we are able to see each star in the star cluster. So what we do is to get the luminosity and the temperature, or the color and the magnitude of each star in the cluster, and make a plot like this. Initially, when the star cluster has an age of about 10 to the 7 years, the figure or the plot that we will get is going to look something like this. So all stars are on what we call the main sequence line. So if you remember, I told you that our own sun is in the phase of the main sequence. And that is the phase that most, or I should say, the phase that is the longest phase in the life of a star. So most stars, when we observe them, the longest phase that we can observe is the main sequence phase. But then after some time, as I showed you in the previous slides, the star will run out of hydrogen in its core. So it's not going to be a main sequence star anymore. At that point, it's going to become a red giant. So as it becomes a red giant, the color is going to shift. So it's going to come somewhere here. And we call this point a main sequence turn-off. This is the main sequence. This is the turn-off point where we see that stars are leaving the main sequence. So now look here, this is the time at an age of 10 to the power 9 years. So you see that initially we had some stars here, but they already died. So they left the main sequence. And then after some more time, more stars are leaving the main sequence. And then at more and more time, which is the age of the cluster, more and more stars are leaving the main sequence. So when you want to make a guess by looking at these figures, you will see that the location of the main sequence turn-off is proportional to the age of the cluster. So if it's up here, that means it's a young cluster. If it's very down here, that means that most of the stars in the cluster have died. So they left the main sequence. Or maybe I should not say have died, but have evolved. So they left the main sequence and they're somewhere here. Okay, so that is the method that we use to study the ages of star clusters if we have data from individual stars. Okay, so that was about the age. Now, how about the metallicity? Metallicity can be studied in different ways. One of the ways that I want to discuss is one of the ways that I used in one of my studies, and that is by using the red supergiant stars. So red supergiant stars are evolved stars, which means that they already left the main sequence, and they have very high masses, and they're among the largest stars in the universe in terms of size. The reason this is very useful is that it means that we can observe it in faraway galaxies. That our goal is always to try to find bright objects that we can observe even if they are in other galaxies. And they're also an important thing about them is that they are young, which means that they can give us information about the early stages in the life of a star cluster. Okay, so the results that I want to discuss here, those are based on a study that I did. So I started basically in summer of 2019 during my visit to the European organization, the ESO, European Southern Observatory, European Southern Observatory ESO, with my collaborators there and other collaborators from other universities as well. We published this last year in September. Okay, so the idea was that we applied for telescope time using VLT. As you might know, VLT is the largest European telescope in the southern hemisphere. So we used the VLT telescope to obtain the spectra of red supergiants in different clusters near the center of our own galaxy. So if you look at this figure here, this is our sun, which means that this indicates our location in our galaxy. And these are the different clusters that we obtained the observations for. The one that I'm going to share the results for, the others are still work in progress, but we have the results for the first one. And the reason we chose the first one, maybe it's very obvious, is that it's very unique. The location of this cluster is different than the other clusters. So we wanted to start with this specific cluster first, so that we can understand the chemical composition of that region near the center of our galaxy. So as I said, we observed different red supergiants in these star clusters. And here I'm showing the spectrum of the 6 red supergiants that we observed in this particular cluster. So what we did is that we tried to find the best match between our observations and the models in order to obtain the chemical composition of these red supergiants, and then take the average of all of them and then consider that value to be the metallicity of that star cluster. So in this case, the metallicity that we got for this, we got both the metallicity of the cluster and a better estimation of the age. This cluster already had an age estimation in the literature, but we kind of like constrained the value based on our results. So this was the first metallicity measurement for this star cluster near the center of our galaxy. One thing that, just so I can move on, just to make sure that whenever we fit for the chemical composition, we of course need to count for other things as well, like the effective temperature, the microturbulence velocity, and the gravity of the star, in addition to the resolution and the radial velocity of these stars. If you look here at the radial velocities, you'll see that they're very close to each other within the errors, and that confirm that these red supergiants are all part of the same star cluster. Okay, so that was the first results that I wanted to share. Now coming back here, so we said that we can use resolved stars, and this is what we did for studying a cluster, or we are still studying the other clusters as well. But I mean that the star clusters that are within our own galaxy can be studied using resolved stars. So we can look at individual stars and then extract information. However, as you can see here in this figure, if we want to go beyond our Milky Way, so if we want to study the Magellanic Clouds, for example, or M31, M33, and even star clusters or galaxies that are beyond our local group, we will need to rely on the integrated spectra, which means, again, instead of looking at spectra of each star, we will have to look at the spectrum of the entire cluster as a whole. And this is part of an ongoing collaboration that I started last year during my visit to Space Telescope Science Institute, and this was part of my sabbatical project. So we started with the first assumption that if the star cluster is big enough, so the mass is good, or it's big enough not to have to worry about the statistical imperfections, then we can take the models that are already there in the literature and try theoretically to see if we can get, using the full spectrum fitting technique, which means that we compare the model, the theoretical models, with our observations to check and see if that will give us an accurate value for the age and the metallicity of the star cluster. That was the first study. The second study, we took the mass in consideration. So we investigated what happens if the mass is not high enough. And also in the same study, the second study, we explored the other ranges, not only optical range, but also the infrared range. And this is very useful. The motivation for this paper was that, as you know, now the new telescope, the James Webb Space Telescope, is going to give us some new insights about these kind of studies. So we wanted to get some preliminary results on theoretical analysis. And then the most recent one, this is just last month in April, we published a third paper in this series, and we discussed the idea of what happens if we have possible age spreads within the star cluster. Would we be able to identify them with full spectrum fitting technique or not? We expect 2 more papers in this series, so hopefully those are going to come out this summer. And so the reason I didn't want to go into the details of this is that they are theoretical, so they're done on very large samples. But I think that generally we like to apply these theoretical studies into kind of like real observations. So that's why here I just showed that the method is correct, so we can use it safely. And now I'm going to show some applications of how can we use the results from integrated spectra of age and metallicity to trace the chemical enrichment history of galaxies. So now I'm going to discuss, after testing the method, I'm going to discuss the results that we got for the chemical enrichment history. So this is a project or a series of projects that started many years ago, and I have to acknowledge that this was organized by ARAS. So I was able to visit Harvard Center for Astrophysics, and I met my collaborator Igor there, and we started our project. Our first paper was published in 2018, and we had a small sample of star clusters in which we tried to reproduce, using observations, what is obtained from theoretical models about the chemical enrichment history. So our goal was to answer the question, can we use integrated spectra to trace the chemical enrichment history of galaxies? The reason we want to do this is that if we can confirm that this is possible for nearby galaxies, for which we have both integrated spectra and resolved data, that means then we can use it safely for galaxies that are very far away from us. So the model that we used was the model proposed by Spitoni et al., in which it gives the chemical enrichment, Z, which is the metallicity, as a function of time for different constants. So one important thing is that this depends on the star formation rate. So we see that the constants that are involved here are the mass fraction of the heavy elements. Those are the ones that form into the star, as we discussed before, and then they are given back into the interstellar medium. Then we have R, which is the return mass fraction of gas, which means that when the star formed, there was a portion of the gas that did not change in chemical composition. This is going to be returned again into the interstellar medium. And we also have the mass, the initial mass of the gas. And we finally, what else? Yeah, we have lambda, which is the outflow coefficient. So this is the model that we used, the theoretical model. And our goal was to see if we can obtain the results from our observations and get the same results that are predicted by this model. So we used a sample of 15 star clusters. 11 of them were observed with a SWORD telescope. And that is, by the way, maybe I should have mentioned this. This is a telescope that I had here on my first slide. Just want to share something interesting about this telescope, sorry. Yeah, so this is the SWORD telescope. And as you can see, the nice thing about this telescope is that it's at a very high altitude. So basically it's above the clouds. These are the clouds, this is not snow. And that's why if it becomes cloudy, we don't have to worry about the clouds. You know, usually when you do observations, you're worried about the clouds and the rain and so on. But this telescope is above the clouds, so we can do our observations. And this is, I was there at this telescope. This is the first time I went to this telescope in, now it's been almost, well, yeah, more than 11 years ago when I was a graduate student. So anyway, so the idea is that using a sample from the SWORD telescope, in addition to 4 more clusters from the Magellan telescope, we had a total of 15 clusters, and we obtained the ages and metallicity of these star clusters. Here, I want to pause a little bit, especially for the students. So one of the things that we struggle a lot as astronomers with is that whenever we want to imagine ourselves as astronomers or as scientists, this is what we think that we do, right? We're trying to unlock the secrets of the universe. And if we look at all these, so this is what my friends think I do. We just use small telescopes and look at the stars. This is what my mom thinks I do, that we're in a lab. This is what the society thinks we do, that we're astronauts. This is what the university thinks we do. They want a lot of publications, but reality is that we do a lot of programming. So if you are stuck with programming and you spend a lot of time doing that, don't feel bad. This is completely normal. So after a lot of programming, we get these results for our sample. We get the age and the metallicity, and this is the different telescope used for the observations. So for this, as I said, we used the full spectrum fitting technique, which means that we had 1 spectrum per cluster. So each cluster represents 1 object, and it has 1 spectrum that we used for obtaining the results. So now, the results that I like to share, this is the results that was published in the 2018 paper, is that if you look at this figure, just so you understand what this means, the red line is the line that we get from the model. The dashed lines are the upper and lower limits, which means that, as you know, the model would have errors. So these are the upper errors and these are the lower errors. And these dots or squares are our observations. The blue ones are the observations that we got with the SWORD telescope, and the green ones are the observations that we got with the Magellan telescope. So what you can see here, and this is a very nice result, is that all our results match the model very nicely. So the conclusion that we found after this study is that we can use observations to trace the chemical enrichment history of galaxies. So the point is that even if we do not have this model, we can still get an idea about the chemical enrichment history of galaxies only by observations. So this is the first result of the paper. However, if we want to be careful, we have to remember something that I discussed early in the presentation, which is that there are different kinds of supernovae. And those happen at different times. So a core collapse supernova would occur 1 billion years before the type 1a supernova. If you remember, the reason for this is that the high mass stars die before the low mass stars. So the first supernova that comes from the core collapse, which is the high mass star, will happen at a different time than the other type 1 supernova. What this tells us is that the chemical composition does not change at the same rate. There are elements that will be enriched. For example, here in this, for the sake of this talk, the alpha elements, which are the light elements like neon, magnesium, and so on, these elements will form at a different time than iron. And that's why the reason we have to be careful here is that if you look at this diagram, I'm using Z for metallicity, which means that I'm considering all elements. Remember what I told you in the beginning, that in astronomy, we take all elements heavier than helium to be what we call metallicity. So here I treated all, or me and my collaborator, we treated all elements the same way. But this is not accurate. We have to be careful that the alpha elements will form at a different time than iron. So we need to make two separate plots. And this is exactly what we did here. We redid this. We first compared the alpha elements and then the iron elements. The iron and the other elements that are iron-like. So you see here now the green line is the one that represents the model for the alpha elements. And you see the green dots nicely matching that green line. And on the other hand, for iron, we have this blue line and these blue dots that represent the iron composition of our clusters. Again, they are matching the model very nicely. So this was a very exciting result, but because this was done on only 15 clusters, we thought that, okay, why not expanding this to more clusters? So as a result, so first I'm going to share the results of this. This was the first evidence, so this was a big deal, that this was the first evidence that we can use integrated spectra to trace the star formation and the chemical enrichment history of galaxies. And the reason this was significant is that if we are confident about this, now we can apply our methods to far away galaxies for which we do not have result data. So now the last thing that I want to discuss are two projects that I'm currently working and I'm going to hopefully be finalizing this summer. One project is about looking into more details. So instead of having a diagram like this of only alpha elements and iron, why not looking at each individual element? So instead of putting them all together, I can take, for example, calcium alone, magnesium alone, neon alone, and so on. So that's what we are currently doing. So for each one of these elements, we're trying to get the correct estimation. And the other, so this is in collaboration with Dr. Svea Hernandez from Space Telescope Science Institute. The other project that we're currently working on is that we obtained more observations from the large and the small Magellanic Cloud. So now we want to redo the analysis that we did on a small scale, apply it for, on a larger scale. And here I'm sharing some preliminary results that have not been published yet. These are our preliminary results, which show that, again, the red line is the model. The blue dots are our observations. So most our observations are within the errors of this model. We're still investigating what's going on with this cluster. And we also did the division between alpha elements and iron peak elements. And again, we see that overall, the green dots are above the blue dots, as expected, because the green model is above the blue model. And then again, there is this exception with this cluster, which we are still trying to understand. And that's it. So.
Thank you, Doctor, for this very interesting and informative presentation. Now we are going to use this opportunity to give a little bit of time to our audience questions. So if you have questions, you can raise your hands. Here there is in Zoom reactions. or we give you a tone. Okay, there is Hamza Labyad asks, is there any difference between the chemical composition, enrichment of our galaxy and distant galaxies?
By enrichment, you mean how it changes, or how it? So the chemistry, or the let me. You said. Oh, so the chemical yeah, okay. So sorry, I just saw the question now. So the chemical composition and the chemical enrichment, so they're two different things. The chemical composition, yes, it changes from one galaxy to the other, and that depends on the enrichment, because the chemical enrichment, as you might remember from that equation for the model that I shared, it depends on the star formation rate. Which means that if we have a galaxy that has a high rate of star formation, the chemical composition and the enrichment will be affected by that. So yes, the short answer for this is that yes, different galaxies will have different chemical enrichment based on the star formation rate in that galaxy.
So we have another question from our followers. What elements did stellar nucleosynthesis?
What elements come from the nucleosynthesis?
What elements did stellar nucleosynthesis?
I mean, so yes, the elements come from the nucleosynthesis. Is that the question? Is it written? Sorry.
He asked, what elements did stellar nucleosynthesis?
Yeah, I mean the concept. That's so the nucleosynthesis produce the elements. So, like all these elements up to iron are produced in the core of the stars.
The second question is, what elements are formed during stellar evolution?
What elements are from the stellar evolution?
Are formed during stellar evolution.
What elements? Yeah. So these are so different elements are formed based on the initial mass of the star. So for the low mass stars, as we saw in that picture, hydrogen is becoming helium, and helium is fused into carbon, and that's it. We cannot get other than that. For high mass stars, we can continue, as in that picture of the different elements, we can continue to heavier and heavier elements.
Here, there is another question. He asked, what causes star formation?
What causes star formation? Okay, so that's a very long, that's actually this in astrophysics, we teach it as an entire chapter. So maybe one short answer is that, so the interstellar medium has, it has a mass distributed over the interstellar medium. However, some places have more mass than the others. So because of gravity, they will start accumulating more and more mass, and then until they finally collapse, forming one mass that is going to start rotating. So of course, the physics of this is in much more details, but this is the general concept.
Okay, there is
excuse me, can I ask a question?
Okay.
Okay, thanks a lot for this very enthusiastic talk, Randa and Maisa and all. I wonder about the facilities to use the very large telescope. Of course, it is online. How did you arrange for that? Okay, this is my screen. This is my camera. Yeah, okay. Okay, Randa.
Yes.
I'm from Oman and from Jordan.
Yeah. So yeah, for the very large telescope, actually this was very competitive, and so I've been applying for telescope time for many years. I sometimes get it and sometimes I don't. I have to apply, so I write a proposal, discussing the science that I want to do, and then this is evaluated by a committee, and then it's like shortlisted, and then they choose the proposals that they think that are going to be the most significant ones for the new science. So that's why applying for the telescope, you need to write a proposal, and you have to be among the top people who are selected for this. So the reason I'm saying this is that it happened, like in some other times, I applied for telescope time and I did not get it. So it's not that whenever you apply, you get it. You have to apply and be lucky to get it.
Okay, thank you. Thanks a lot. That's wonderful.
Yeah.
Dr. Duha Mahmoud is asking in the chat.
Okay, I see. Yes, correct. So this is for our sun and for low mass stars as well. Yes.
Another question from Hamza Labayid. What's the idea behind trying to study metallicity of individual elements?
You mean the amount of the, so we are studying the metallicity of galaxies by analyzing different individual elements. So I think you mean, why do we want to study the different elements, right? The individual elements? Yes, okay, yeah. So the reason for that is that when we understand the origin of these elements, we can know how the history. So both, we have two histories. We have the stellar formation history, and we have the chemical enrichment history. So we want to see at what rate, for example, is it uniform that along all the galaxies we have the same rate of star formation? And how is that star formation related to the different elements that are being formed? So this gives us about the overall understanding of the universe, of how things are happening at different rates and at different locations in the universe, at different environments, because each galaxy has different environments. It could be a region where it's very violent in terms of star formation, and it could be a place where it's not that active in terms of star formation.
So we have another question from our followers. Will stars stop forming one day?
What is it? I couldn't hear it, sorry.
Will stars stop forming one day?
If stars are forming in one day?
Will stop forming.
Stop forming, okay. If stars will stop forming one day, I mean, as long as we have the current environment and the current conditions, I don't think that they can stop completely. Now, they might stop, for example, in a certain region. For example, like if our interstellar cloud becomes the density of the interstellar cloud becomes very light, which means that there is not enough material to form stars, then yes, that is possible for that specific region. But if your question is if it's going to start everywhere in the universe, that, I mean, unless the universe becomes, the density of the universe becomes very, very, very low. So there is not enough material to accumulate to start stars, to form stars.
Yeah. Okay, there is another question. What does nuclear fission have to do with the birth of stars?
With the birth of stars?
Yeah.
No, so all the nuclear reactions happen in the core of the star. And actually, so when we say that a star is born, that is when the nuclear reactions start in their core. For example, if we have a mass that has all the elements that a star would have, but they do not have nuclear reactions in their core, we cannot call it a star. So stars are born when nuclear reactions happen in their core. For example, planets, there are big planets, like for example, Jupiter. Jupiter is a very big planet, but it has no nuclear reaction in its core, so we cannot call it a star. So by definition, to have a star, we have to have nuclear reactions in the core.
Okay, it's clear. There is another question, Doctor, if you... What gases are needed to produce the new star?
What gases are, I mean, so the interstellar medium is mainly made of hydrogen and helium. So these are always there in the interstellar medium. Now, the rest is going to decide what the composition of the star is. So the condition for forming stars does not depend on the type of elements or type of gases. We just need to have enough mass for it to accumulate and start a new star by free fall.
Okay, there is another question here. He is asking about where in the galaxy are the most stars born?
It depends. So there is, again, it depends on the density of the interstellar medium at that location. So if it's a very dense location, then we expect to have many stars. If it's not that dense, we do not expect to have many stars forming.
Okay. Another question. How hot must a star get before it becomes a star? And why does it need to get so hot?
Okay, so it's true that stars are very hot, but the reason is not that they need to become hot to become stars. The point is that as the material, you can think about it in terms of physics, as the material accumulates in a small region, it's more and more pressure, and normally when you have more pressure, that increases the temperature. So it's not because stars have to have a certain temperature, but it's just natural that it's happening because of the pressure that is added to this new formed star. And as this temperature increases, now the temperature is right for these nuclear reactions to start. If the star does not reach that temperature in its core, it will never become a star.
So there is another question here. Okay. How long does it take to produce a star?
It depends. It depends on the mass of the star. So, of course, this is going to be very long times. It depends on the initial density of the cloud. So it depends on many factors. And that's why maybe one thing that I should mention, so when we say that, for example, star clusters have the same age, we don't mean that they necessarily formed or were created at the same exact time. But roughly speaking, of like when we look at the age of the universe, we're talking about, big scales of time. So within the same time scale, these stars formed. So they take time to form, but not necessarily on the same day or even on the same week or the same year. So it takes many years to form.
Okay, I think that's all the questions I received from our followers. Is there any question from our audience? So I think there is no more questions, Doctor. So thank you so much for your time and for this interesting lecture. And I would like to thank our audience also.
Oh. Yeah, thank you so much, and I hope that this was useful.
I think Hamza Labayd also have another question.
Oh, I see. Let me check. Is it safe enough to use integrated spectra for clusters to study metallicities? Is there any reason for different metallicities inside one cluster? Yes. So two questions. Yes. The first question is it safe to use integrated spectra to study metallicity? The quick answer, I can say yes. And this is what we, as I told you, I did some theoretical studies on this, and I showed that we can use integrated spectra to study both the age and the metallicity. So that's the first question. The second question, is there any reason for different metallicities inside one cluster? Now, there are two things. One is that these differences in metallicities might be real, and that is because the details. So we say that roughly we have the same chemical composition, but the chemical composition might be different from one location to the other within the same cluster, because of course we're talking about the star cluster is huge. The other thing which we need to keep in mind is that the differences that we see in the measures of the metallicity from one star to the other could be because of the errors. There are different errors there. For example, the resolution or the quality of a spectrum that we get for a star might be not as good as the other star. So that's why whenever we have measures for the metallicity, we have the errors so that we can compare these stars, and usually they are within the errors. So the entire cluster has the same metallicity within the errors.
So I think that's all question we have today. So I would like to thank you, Doctor, and thank our audience to join us today. So
yeah, thank you so much for the hard work, and thank you for everyone who attended this. And yeah, I'm happy that it was like a nice discussion in the end. So if you have more questions, always feel free to contact me or contact the organizers and they can ask me.
thank you.
شكرا.
Bye.
Bye bye. Bye bye.